Lab 2 report for Physics 22102. Instructions of the lab. The purpose of the lab was to use purposefully charged tape in order to compare the point charge model from Lab 1 to the line charge model done here in Lab 2. This is done by dividing the tape up into segments and treating each segment as a point charge evaluated over the entire line. The procedure included pulling the tape off of each other to leave an excess charge in both the tapes, and we use the equilibrium positions and forces to determine the charge of the tape, and use the momentum principle to find the magnitude of the charge. The fundamentals of this lab included distributed charges for a line, Newton's second law, which is F equals ma, Coulomb's law, which is F equals QE, electric fields, which is E equals KQ over R squared times R hat, and where R is the distance between the observation point and the evaluated point on the line, and using superposition to find the charge distribution. The experiment consisted of using the force, field, which is shown here, and the charge on the tape was around 6.8 times e to the negative 8. Using the superposition of these segments on the line will give us a better approximation for the entire tape. The system here is tape B, and the surroundings are everything else. Initially, both pieces are neutrally charged and gain charge while being ripped off each other. Tape A was placed underneath tape B to determine the distance where tape B floated up in this experiment and then calculate its charge. Our calculations included some assumptions. First, that we assumed that the tapes are equally distributed line charges and the tapes are equally charged at every point, and that the only forces acting on them are electric and gravitational, which is not necessarily true. So then F net was equal to 0 because nothing was moving. So the force of the electric field minus the force of gravity is equal to 0, meaning the force of electricity is equal to the negative gravitational field. This means that Q equals the square root of mgr squared over K, which means that this is the math here. There's some possible sources of error. One is that air resistance, and the other is that every piece of tape doesn't have the same charge. Here are the lab results. So the length of one of my pieces of tape from the last lab was 20 centimeters. Mass then was 2e to the negative 4. The distance between these two pieces of tape when one began to float was 0.3 meters, and the magnitude of the gravitational force on the floating piece of tape is 1.96 times e to the negative 3, and the magnitude of the electric force is negative 1.4 times e to the 8. Here's the coding. As shown, the magnitude on one charge on my piece of tape, as calculated by the computational model, is 8.57569 e to the negative 4th. There were some assumptions and approximations. One was that I ignored air resistance on a moving object. I treated a long tape as if it was a point charge, and I assumed that the E tape was around the same length of charge. As far as the questions at the end go, what if we had modeled all of the tapes as a single point charge like in the previous lab? If you do that, then if you model it as a point charge, the electric force and gravitational force are not equal, whereas modeling it as a line charge makes them closer to equal. These estimates differ because the line charge accounts for the charge distributed along the entire length of the tape, and this